using the book I have, which is called Power Analysis Attacks. Very nice book, and you know how to get it. I told you, you just go to the university's library catalog and you type in Power Analysis Attacks, and you can get the PDF. You don't even have to pirate it. It's so nice. You don't even need a proxy. So in the Power Analysis Attacks book, there is a definition of Power Analysis Attacks. And now let's look very closely at this definition. So the definition is like this. Power analysis attacks are cryptanalytic attacks that allow the extraction of secret information from cryptographic devices by exploiting the power consumption characteristics. Now, this is quite a deep statement. Let's try to read into it. So first of all, from what do we extract the secret information? From what? From cryptographic devices. So, device and not what? Device and not algorithm. Okay? We're not attacking the algorithm, we're attacking the device. If I come and tell you, listen, your phone is running RSA and I broke your RSA encryption on the phone, does that mean I broke RSA? No, it means I broke the phone. Okay? So I break implementation. What else? Device and not the user. So there is no social engineering or keyloggers or something like that. So this is the second thing which you can learn from this. And now, what kind of devices? Cryptographic devices. Cryptographic devices. So what secret information do cryptographic devices have? Keys. Yes, they have the key. They have keys with the Z. Thank you. They have key, and this book is all about keys. So keys are really nice for us to talk about because they have beginning, end. You can extract half of the key. You can make it stronger by making the key longer, and so on. So this book is about keys. Personally, my research is looking at things which are not keys, which you can steal. For example, health information. If the fact that somebody in my building has coronavirus, so that's a secret, right? It might be we might be able to extract it using power analysis, but I'm not very clear about how we can make the key longer to protect against this risk. Right? But can I make the coronavirus longer? So secret information cryptographic devices is keys. But again, I think that other things can be attacked by side channel, and I think we'll see some of that when we talk about microarchitectural attacks as time goes. So the last thing I want to talk about here is that I'm exploiting the power consumption characteristics. What does that mean? It means that I'm not necessarily measuring their power consumption. Okay, so it's an effect of the power consumption. I could also be measuring the EM radiation. I could be measuring the magnetic flux, but something which is affected by the power consumption. And the natural thing, as you see on the front page, is measuring power consumption. But again, I'm using the power consumption to do my attack. I'm not necessarily measuring it directly. So OL, can we attack every length of RSA? Every is a theoretical claim. If you can attack RSA in linear time, then you can attack any key that takes the linear time. Okay, so let's say you might not be able to attack 1 trillion byte RSA, but there is a question of whether you would want to do that at all, because encryption is also very slow. So, but in theory, once you get power analysis done, and assuming there are no errors in your encryption, in your attack, then the length is really effective. Not really effective. So let's continue. So there are two ways of doing power analysis, two kind of thoughts. One of them is called low data complexity, and the other one is called high data complexity. And low data complexity means I just get a little amount of measurements, and high data complexity means I get a lot of measurements. And data complexity is a complexity measurement that you're less used to, What is the complexity you usually learn about in when you learn complexity in class? When I say complexity, what do you mean? Well, yeah, time complexity, exactly. So low data complexity attacks tend to have high time complexity because that's how it is. And high data complexity attacks tend to have low time complexity or computational complexity in general. But we'll see. We'll see. Now, this week I'm going to show you a simple power analysis. And next week, our honorable guest lecturer will also show us a very, very fascinating application of simple power analysis. So, how do I do it? I take the device, I measure the trace, I analyze the trace, one trace, I get the key. Great. So, why? Let's talk about the properties of this attack model. So first of all, it's very reasonable. So it's reasonable to assume that I can measure my device on the test doing one encryption. Because high data complexity power analysis, also called differential or correlation power analysis, requires sometimes that I make 1 million measurements, 1 million or 10 million measurements. So it makes much more sense that I can take one measurement than saying that I should take 10 million measurements. Of course, it can be justified. Let's assume I have a server, nobody's watching it, and I can ping it 1 million times a second. In 10 seconds, I'll have million measurements. But if I have a device, the devices I need to maybe push a button, one trace or two traces a measurement. That's more makes more sense, and it's easier to explain also to my systems architect. If I get a simple power analysis attack done, it's kind of easier to justify defending against it. So what are the disadvantages of this? Oh, here is a very nice attack model. So this is what you see here. I'll show you the movie soon. What you see here is it's a device which is designed to attack a payment system. But we don't want to attack the payment card. We want to attack the payment network, the payment terminal. So if I wanted to attack the card, it would be very easy to do any kind of high data complexity power analysis. Why so? Why is it easy to attack the card? Yeah, I own the card. It's my card. I can, the worst thing that will happen, I will break it and get a new one, right? So I can even, melt it. But if I want to attack the payment network, and let's assume I want to do power analysis on the payment network, on the payment, on the terminal. So I can't really melt it or steal it because it's in the store. I might be able to touch it or interact with it. So now, thanks to the corona, we're getting this in Israel as well. I think you've gone to the store. Those of you who have gone to the store, you know that at least in some stores now, if you want to pay, the cashier doesn't want any of your germs or your card. You take your own card and put it in the terminal, and then you're finished. So I can't do anything crazy with the. We hate the camera. Yeah, we can't do anything crazy with the terminal. We can't melt it. We can't cut it. But what we can do is use this very fancy device. And this device actually was built to do a different attack. It was built to do a relay attack. And I want to show you a very cool movie. Okay, I'm going to show you a nice little movie. And I know that I need to paste the path into the chat, so I'll do it. So this is a result by a university in the UK.
This is controlled from a laptop and runs software written by the team. All of this is hooked to a fake card, which stops into the actual shop terminal.
So these two guys are Stephen Murdoch and Sal Dreamer. and they're in Cambridge. And they're doing something which is called a relay attack. If you want to learn about relay attacks, there's a Black Hat talk by Stephen Murdoch, which is fantastic. But you can they're going to build a relay. Relay means that the smart card thinks the terminal thinks it's talking to a different smart card. But I just want to show you the electronics of it.
It wouldn't have to be this big. He was already working on miniaturizing it into a unit the size of a remote. Carl has a trick up his sleeve. Dummy card has a concealed cable running up his arm to the kit in his backpack. So will it work? He doesn't need to know the actual pin from the stolen card. Any combination should do. The stolen card is getting a message that the purchase has been authorized by signature. This mismatch should allow the transaction to go ahead. And yes, it does. The printout states it's been verified by PIN. In fact, SAR tried a handful of high street debit and credit cards, keying in 0000 as the PIN, and it works every time.
So again, I have to note that they're not doing a power analysis attack, but the test setup, if you want to do a power analysis attack on the payment terminal, would be very similar. So I'm not sure you noticed, but SAR has this very interesting looking card, which is actually connected to a serious computer in the back. So you could have this device measure the power consumption of the pet. But again, you can't do this a million times. You can do it once or twice, and then you have to go home and look at the data you captured and try to think about the key. So this attack model is reasonable in many cases, even in these very science fiction and exciting cases. So what are the cons? The cons are that you do need to know a lot about the device under test, because you only get one trace. So you need to be very, very well prepared to deal with this trace. Just for example, when is the encryption happening? When does it begin? When does it end? What does it look like? How do the bits look like? How do the values look like? What do the instructions look like? So you need to get a lot of reverse engineering done, and you need to have a very good model of the device under test, and sometimes that's not reasonable. And another thing is you might need a really good signal-to-noise ratio. What does that mean? I only get one measurement, right? So let's say I have this amazing machine that you feed in this measurement, and look, out comes the key. I get like 128 bits of key. And now I put my measurement into this machine, and out came 128 bits. Let's say it's a 128 key, 16-byte key. And so is this the right key? Let's assume I can check. How can I check if it's the right key? Maybe I have an oracle, like a decryption. I have like a plain text and ciphertext I prepared ahead of time. I can check if this is the right key. Okay, if it's the right key, awesome, I'm happy. What if it's the wrong key? What do I do then? It's the wrong key. Why would it be the wrong key, by the way? Why did my machine break? Yeah, there was noise. Yeah, right. There was noise. I'll try to cover a little bit about the noise later. But there was noise, so the machine thought that there was a 4 and there was a 5. So what do I do? How do I deal with it? So maybe I can try flipping a couple of the bits. Maybe I got close to the key, right? Maybe one of the bytes was different. So let's say I have a 16-byte key, and I'm very optimistic about my machine. I assume that it got 15 out of the 16 bytes, right? And one of the bytes is completely. I can't measure again. No. I'm home now. I'm home with my trace and my crime. So my machine got 16 bytes of the key. It got 15 bytes correctly, and one of the bytes, it got completely random. So what am I going to do? I'm going to try and undo the error and doing my trial decryption. So I'm going to try candidate key. Yeah, so I'm going to try 16 times 256. This still sounds reasonable, but what happens if only if 2 bytes go wrong or 3 bytes go wrong? It goes downhill very, very fast. So the signal to noise ratio is really a showstopper. And to counterbalance that, to try and get the key using high data complexity, high time complexity methods, because now I'm iterating, I'm kind of doing a dynamic search away from the correct key. This could take so much time that it's not reasonable. So if I take my measurement, it takes me one trace, and then I have to sit 1 month on the decryption. Then again, it's not very okay. It depends on the attacker model. But if I'm trying to, for example, get on the bus for free, I don't want 1 month of processing. Fine. So as I told you, there are other types of power analysis attacks, and the division is low data complexity, which require you to, this one is קשה באימונים קל בקרב, this one. So hard when you're training and easy when you're attacking. So you need to really prepare yourself very, very well. And let's see how much we can cover this year. And the other one is high data complexity, which is just קשה בקרב. So you get a lot of data, and then hopefully with statistics and some reasoning, you can get your data out of it, you get your key out of it. So let's have